This week, we'll look at the surface of the Earth, the landforms and processes that make the terrain on which we live. In this first video, we'll look at the lithosphere, mainly the plates that make up the crust. The shape of the land affects human settlement patterns, determines habitable areas, natural hazards, available resources, agricultural potential, and even transportation possibilities. The Earth condensed and congealed about 4.6 billion years ago from dust, gas, icy comets, and other space debris. The crust began to form. As the planet solidified, materials were sorted by density. Iron moved inward toward the core, silica moved outward toward the crust. The Earth is therefore made of concentric layers, each of different chemical composition or temperature. Differential transmission of seismic waves proves this information. The lithosphere includes the crust and the upper section of the mantle that affects the crust. The distance from the center of the Earth to the crust is about the same as the distance from Anchorage, Alaska to Miami, Florida, or about 4,000 miles. The crust is thinnest in the Pacific Ocean, about 6 kilometers, and a project is underway to conduct drilling there so we can gain detailed knowledge about the mantle and how it impacts the crust. We have the technology to drill that far, as evidenced from these examples, but the project is not yet fully funded. As mentioned, the lithosphere includes the crust and the top part of the upper mantle. The crust varies depending on whether it's under land masses or under the ocean. Continental crust is thicker and lower density than oceanic crust. The crust in the Pacific can be as thin as 6 kilometers, and the continental crust can be as thick as 60 kilometers. Rocks and minerals make up the crust. Rocks of the Earth's crust vary according to mineral composition. Minerals are a particular chemical combination that has a hardness, density, and definite crystal structure. They are made up of particles that contain various combinations of common elements and less common elements. Rocks are clusters of minerals formed by heating, cooling, and deposition. We'll look at each of these in more detail, but the three types of rock are connected. Igneous rocks are formed as molten material cools. Exogenic processes wear this down and redeposit it as sedimentary rocks, and heat and pressure transform these into other types of rock. Most of the crust is composed of igneous rock. Igneous rocks are formed by the cooling and hardening of molten material. Molten material from the asthenosphere escapes to the Earth's surface via weaknesses in the crust, such as volcanoes or fissures. When the molten material cools, it hardens and becomes rock. Intrusive rocks are rocks that form below the Earth's surface and are ejected to the surface or exposed by weathering or other processes. Extrusive rocks are rocks that form above the Earth's surface in the open air, such as lava. Sedimentary rocks are formed of fragments of gravel, sand, silt, and clay that were eroded from already existing rocks. The weight of enormous amounts of sediment may cause interlocking of these grains and therefore lithification. It accumulates in layers called strata over time, and is the only rock type in which fossils are preserved. The most common environments of deposition are rivers, lakes, oceans, tidal basins, and deserts. Stratigraphy is the study of the sequence, thickness, and distribution of rock strata. The law of superposition states that lower strata are naturally older than upper strata because of the order in which they were deposited, in rock formations that are not deformed by other processes. Some sedimentary rocks contain clasts, or fragments of other rocks, while others are made of dissolved minerals that precipitate out of water, sort of like when you let a glass of water evaporate and you see that mineral film on the glass. Clastic sediments are formed when rocks, or clasts, are trapped in sediment, which is also usually made of weathered rocks that are more broken down. Organic sediments, such as coal and some limestones, are formed when plants and animals decay and are compressed over a long period of time. Minerals that are water-soluble are deposited through evaporation and form chemical sediments. Rocks that have been drastically altered by heat or pressure deep within the Earth's crust are called metamorphic rocks. Like igneous rocks, metamorphic rocks are composed of crystals. Because of remineralization in the rocks, minerals of the same type tend to cluster together. This creates a band in the rock, but should not be mistaken for the strata of sedimentary rocks. In this instance, we see limestone become marble and shale become slate. Both of these are much more durable and usable in their metamorphic form. Here also, sandstone becomes quartzite and slate becomes phyllite. Geologic processes move slowly. Landforms evolve over millions of years. As mentioned, the Earth is about 4.6 billion years old and changes very slowly. The geologic timescale shown here is determined by the layers of rock and is delimited by major events, such as mass extinctions or significant geologic changes. In the early 1900s, Alfred Wegener discovered that there were rocks and fossils that are identical, that occur on different sides of oceans, such as the Appalachian Mountains and Scottish Highlands, or formations in South Africa and Brazil. And if you look at the shape of the continents, it does look like they might fit together like a puzzle. In fact, there's a puzzle activity in the resources section of this module you can try. To explain it, he developed this theory that there was one master continent, Pangaea, which broke apart and gradually drifted into the shapes that are familiar today. Here we see Pangaea, the hypothetical master continent from which the others were formed. From the fossil records, he then speculated that this broke into two continents, Laurasia and Gondwanaland, during the Triassic period. The Jurassic period saw the start of our recognizable continents, and you can definitely see where we're going from here. The scientific community thought this theory was ridiculous. Continents don't move. Then, a few decades later, it was discovered that the Earth's crust is made up of separate plates floating on top of the molten mantle. In the 1950s, technology had advanced so that scans of the ocean floor were possible. These scans detected mid-ocean ridges in ocean basins with parallel bands of rock on either side. These mountain ranges were volcanic and so produced new igneous rock on the ocean floor, basaltic rock. If new crust was being created along mid-ocean ridges, then the Earth would have to be growing larger, unless the crust elsewhere was being removed. But where does the old crust go? The idea of subduction zones was first written about in 1962 by Bob Coates, who was investigating volcanoes in Alaska. Here, you can see the plate boundaries and their types, which we'll look at in a minute. Convection in the mantle, similar to our atmospheric circulation, causes these plates to move, and the plate boundaries are connected to the landforms that sit atop them. The video linked here is also linked in your Canvas module, which shows how these boundaries interact, as well as the general motion of the plates and continents. So the discovery that the Earth is covered in plates that move meant the idea of continental drift was not ridiculous, but in fact entirely likely. This is oversimplified, but again, geographers are really only concerned with how this impacts the surface. Heat moves from the core toward the crust by conduction and convection, creating currents similar to our atmospheric circulation, but underneath the crust. The plates float around on top of this and are moved by this motion. Some plates are made of continental crust, some are oceanic, and some are a mix. How the plates behave as they bump into each other determines the type of tectonic activity and land formations which result. Volcanoes, earthquakes, mountains, cracks, etc. are all a product of plate tectonics. There are three basic plate boundary types. Convergent plate boundaries are where plates move toward each other. Divergent boundaries are where the plates move away from each other, and at transform boundaries, the plates slide along horizontally. Let's look at each of these. At a convergent boundary, subduction is occurring. One plate is forced under the other and eventually melts, causing volcanoes. Ocean plates are denser than continental, so they always push underneath. The subduction itself can often cause mountain building by folding up and crumbling the edge of the plate it's sliding under, and earthquakes are also common. Convergent boundaries can also occur when two ocean plates or two continental plates collide. They each result in slightly different mountain patterns, but the general result is the same. You can simulate some of this with brownies. Shove one underneath the other and watch what happens. Orogenesis is the process of mountain building, which happens at convergent boundaries. When two continental plates collide, the upper plate is folded, and some of the lower plate is scrunched up as well. When an ocean plate subducts underneath a continental plate, or another ocean plate, a trench is formed, and volcanic mountains are formed. At a divergent boundary, the plates are pulling apart. As they pull apart, magma escapes through the crack and builds new crust. To continue our brownie tectonics, this time grab the opposite edges of your brownie and pull. Stop before it tears all the way through and observe the rift valley you made. The Mid-Atlantic Ridge is one of the most dramatic examples of a divergent boundary, and it runs up through the center of Iceland, where it's also visible above water. Transform boundaries slide along each other. Often these are in conjunction with other boundaries, where parts of the crust get stuck and then suddenly shift. The San Andreas is perhaps one of the most famous examples of a transform boundary. Like many transform plate boundaries, landscape features along the San Andreas include linear features like ponds, ridges, escarpments, and valleys where areas have settled along the break. Some streams also appear to jog suddenly sideways. Notice in the Wallace Creek image how the natural drainage features have shifted from their original position. For our last example of brownie tectonics, take two brownies, your friends if they're not very observant, and lay them flat on a plate. Now slide the edges alongside each other and note the crumbling and tearing. Dispose of the evidence. The crust can also move vertically as it adjusts to weight added or removed from it. These are called isostatic adjustments. We noted earlier that continental plates are lighter than oceanic plates, but piles of sediment or the presence of glaciers can weigh it down, causing it to press down on the mantle. In the next video, we'll talk about how these plate movements create landforms.